Hello everyone, this is Naman Manchanda and in this video we'll be continuing with the project 2 of Nand2Tetris. So the centerpiece of the computer's architecture is the CPU or center processing unit, and the centerpiece of the CPU is the ALU or arithmetic logic unit. In this project we will gradually build a set of chips culminating in the construction of the ALU of hack computer. All the chips built in this project are standard except for the ALU itself, which differs from the one computer architecture to another. So we'll start off with the adders. An adder is a digital circuit that performs addition of number in many computers and other kinds of processor. Adders are used in the arithmetic logic units or ALU. They are also used in other parts of processor where they are used to calculate addresses, table indices, increment and decrement operators, and similar operations. So the first adder we'll be discussing today is the half adder. The first step on our way to adding the binary numbers is to be able to add two bits. Let us call the least significant bit of addition sum and the most significant bit carry. The function sum AB and the carry of AB happen to be identical to standard XOR of AB and the AND of AB boolean function respectively. Thus the implementation of this adder is straightforward using previously built XOR and AND gates. So basically, as you can see here, the sum, the least significant bit is the result of the XOR operation of A and B, and the most significant bit, the carry bit, is the AND operation of A and B, and this will be the truth table we should be getting. So let's see the code for this. So as you can see, the code is implemented using one AND gate and one XOR gate. So let's run this in the hardware simulator. So I'll be loading the code we just saw. This is half adder. I load the script for it. Now when we run it, now as we see the output, it is same as the truth table shown in the PPT. So our desired output is same as the truth table. Hence our implementation of our half adder is correct. Let's move on to the next adder, that is full adder. It is designed to add 3-bit. Like the half adder case, the two full adder gra- chip produces two outputs, the least significant bit of the addition and the carry bit. A full adder chip can be implemented from two half adder chips and one additional simple gate. A direct implementation is also possible using one XOR and one 3 and one OR gate. So as you can see in the figure, the sum bit is actually the XOR of all the bits A, B, and C, and the carry bit is the OR of all the like ANDs of all the operations. So this is the truth table we should be getting, and let's see the code for this. So as you can see, we use two half adders and one OR operation. Let's load this chip inside our hardware simulator. We load the script now. Let's just run it. Now when we check the output, now when we check the output, it is same as the table shown here, table shown in the PPT. So our full adder is implemented successfully. Now some of the applications of the adders is add 16 or increment 16. So adder 16 is basically memory and register chips represent integer numbers by n bit patterns, n being 16, 32, and 64, and so forth depending on the computer platform. The chip whose job is to add such numbers is called multiple adder or simply adder. Designing to Designed to add two 16-bit numbers. Adder 16 is implemented using 16 full adders. So as it says, we'll be implementing 16-bit adder using 16 full adders. So let's see the code for this. As told, we are using 16 full adders to implement the 16-bit adder. Now we'll load this chip inside our hardware simulator. This is add 16. This is the script. So now we'll run it. Now when we check the output, this is the output we should be getting, and when we compare it, as you can see, there is no values change. That means our implementation was correct. Let's move on to the next application, that is incremental 16-bit. It is a convenient to have a special purpose chip dedicated to adding constant 1 to a given number. Here is a specification of a 16-bit incrementer. 60, it is implemented using 16 half address. So basically what it says is, uh, it is like very convenient to have a specially designed chip to increment 1 to every 16-bit number, because it is very useful in scenarios, different scenarios. So as you can see, like, it was shown that we'll be using 16 half address. So let's just load this chip inside the wait let's just load this chip inside our hardware simulator. Once we load this chip inside our hardware simulator, let's load the script now. Let's check the output for it. Now when we check the output, and if we use compare, as you can see, there is no values change here. That means our 16-bit adder 16-bit incremental was implemented successfully. Now we move on to the last chip, that is our ALU. An arithmetic logic unit is a combinational digital electronic circuit that performs arithmetic and bitwise operations on integer binary numbers. This section describes an ALU that will later become the centerpiece of specific computer platform called Hack. It is implemented using a set of basic logic gates as well as their multi-bit and multi-way variations. So basically the ALU will be implemented using all the chips that we have built till this stage. Net just check the code for the ALU. As you can see, we are using all the chips built in now: Note 16, Mux 16, Add 16, and their A2A counterparts or not. So let's try to load this. We load this chip and we load the script for the same. It will take some time to run the script because it's a big script. And as you can see, the values constantly keep changing according to the script we are implementing. As you can see, our comparison ended successfully. Let's move on to output. So it is a big output. Let's just compare it, and as you can see, there is no values change in the comparison. That means our ALU was implemented successfully. That is it for project 2, and that is it for project 2, and thank you for providing me with this opportunity.